At the core of this project, I describe the use of drones to fulfill tasks that have the possibility of injuring either party involved in an emergency. These drones could be small, in order to navigate tight hallways in police operations, or be large enough to carry medical equipment to remote locations. Now, let's find out just how I plan to illustrate this. I will build a drone that can be activated remotely to take off carrying a life-saving payload, such as an EpiPen, antivenom, or compact CPR kit, and deliver said package to an area in the time it takes for emergency response teams to pull the ambulance out of the parking lot. Let's take a look at how we can get a proof of concept without a small loan of $1 million. To perform the initial simulations, we're going to be using a program called Mission Planner. Mission Planner is an open source project developed to control all types of remotely controlled devices. It provides an adequate overview of telemetry information and GPS data, but it can also be used to program waypoints and specific missions. Let's take a look at how we would go about doing this. First, we need to open up Mission Planner. Here you can see a map of Australia, where I've set up a mission to go from the RAH to a random suburban location. In this scenario, we're going to be taking off from the helipad. I've also identified a car park where it might be suitable to land a drone of this type. Here you can see the different waypoints that I've set up. These waypoints all trigger different events in the drone's journey. We have takeoff, then a waypoint, a delay to keep the drone in the air, another waypoint, then the fifth waypoint is the gripper waypoint, which is where we will release the package that we're currently carrying. After that's done, we'll just return to home and land. You can see that the drone has armed and is currently climbing. Pay attention to the altitude indicator. Once the drone reaches an altitude of 100 meters, it will go towards its next waypoint. You can see that the drone is moving at a speed of 15 meters per second. That's over 50 kilometers an hour. It's amazing how fast you can get places when you don't have to worry about traffic lights. Just a disclaimer, after I've set the mission, I haven't touched the keyboard. This is doing it all by itself. Once the drone reaches its waypoint, it will lower to a height of 20 meters off of the ground and release its payload. After that, it will hover in place and rise once again to a height of 100 meters. Here we can see the drone lowering itself down. It's come to a stop over the waypoint and is currently descending to 20 meters. Once it reaches roughly 20 meters, take a look at the mission logs to see the gripper release. Once the drone raises back up, it will return to the launch position and softly land on the ground. Now, I could have stopped there, but I didn't, because I thought, maybe this isn't enough. I think I need to see this drone in 3D space. I used a plugin called Gazebo and about 1 million dependencies to model this drone in 3D space. This allowed me to do things like create weather patterns and see how the drone would react. Along with this, it taught me more about the Linux command line than anybody really needs to know. I'm going to gloss over this next bit, because I really want to get to building the drone. First, I installed an application called Q Ground Control. I then went ahead and installed all of the dependencies required for Gazebo to function in parallel. After that was done, it was a matter of linking the two together so that the inputs made in the control software were reflected in the simulation. However, Q ground control was using a firmware called PX4, which is slightly more user-friendly. I did not like that. I opted to use a firmware called a1812812, which is highly customizable and open source. After literally hours of digging, I found the required dependencies and installed them, but of course, that did not work. To compile this Frankenstein of a simulation, I needed to edit the source code a little. But once it was over, you could successfully see the mission that I had planned out in Q ground control using a1812812 firmware, reflected in the 3D simulation software. Once the drone has been modeled in 3D space, now it's time to get to building the real thing. Here's a quick list of the main items I used to build this drone. The flight controller is the brain of the drone and is responsible for communicating with each individual component. It also has an ADS-B receiver to be able to route its path around existing air traffic in the area. What good is brains without muscle? These motors, when paired with the right propellers, can produce up to 2 kilograms of lift per motor. These basic radios are used to transmit data such as altitude, orientation, motor speed, onboard temperatures, and more back to the ground station to be viewed by the operator. If you fail to prepare, you prepare to fail. This radio is a backup in case I'll need to override the mission and take manual control. The Raspberry Pi will be used as a bridge and allow me to do things like run custom Python scripts and add 4G functionality to the drone, allowing it to transmit even when it's out of range of the other two radios. This project was a way to build on my previous knowledge with new applications. It was my intention to show that drones are not just toys, but have real-world uses. Today's emergency services are limited by an infrastructure that was designed under different circumstances. By using drones, we minimize first response times, minimize casualties, and extend the area of effective care. Bringing this drone to life presented many problems. The physical aspect of a machine is not something that can be easily simulated. Things like structural stability, battery life, and environmental conditions proved to be great barriers that I needed to overcome. Within this project, the planning phase was the most important. Unfortunately, I didn't give it enough attention. If I were to start over, I would make a concise parts list and make sure that the prototype was airworthy well before the due date. One motivation of this project was preaching system reliability, which was difficult to accomplish with second-grade parts. It was only after I sourced industry-standard parts that the project really came together. My main sources were forums across the internet and tutorial videos for specific component setup. The rest of the project was mainly me tinkering around and seeing what would work.